In the previous video, I mentioned that the fast Fourier transform is an algorithm that evaluates a polynomial p of degree less than n at n roots of unity, where w is the nth primitive root of unity. To understand this statement, you need to know what a polynomial is, what the degree of a polynomial is, what the roots of unities are, and what is a primitive nth root of unity. So in this video, I'm going to explain what a polynomial is, what it means for a polynomial p to have degree less than n, the nth roots of unity, and finally the primitive nth root of unity. So let's begin by defining what a polynomial is. A polynomial is an equation of the form a0 plus a1 multiplied by x plus a2 multiplied by x squared plus a3 multiplied by x raised to the power 3, so on all the way up to, let's say, n minus 1. So there are n terms starting from 0 to n minus 1. These variables that you see in blue are called coefficients. In this video series, you can think about these coefficients as simply numbers. I'm going to be teaching you fast Fourier transform in the context of finite fields. Moreover, the finite field that we're going to be working with is called prime fields. Basically, we're dealing with numbers with x mod p, where this p will be a prime number. And what this means is that we're basically going to be doing addition and multiplications on numbers between 0 to p minus 1. So all of these coefficients, a0, a1, a2, a3, all the way up to a minus 1, you can think about it as a number between 0 to p minus 1. And what goes inside this x? This x will be an element in the finite field. In our context, we're going to be working with the prime field. So again, x will be one of these numbers between 0 to p minus 1. So that is polynomial, basically an equation of this form. So now that we know what a polynomial is, what is a degree of polynomial? What does it mean for a polynomial to have degree less than n? The degree of polynomial p is the highest power of x where the coefficient a of I is not equal to 0. So looking at this equation, and let's say that a to the n minus 1, the coefficient a to the n minus 1 is not equal to 0. It's a number between 1 to p minus 1. Then in this case, the degree of this polynomial will be n minus 1. Since the highest power of x with ai not equal to 0 in this expression will be n minus 1. Let me give you one example of a polynomial and a degree of polynomial. So let's say that we have a polynomial p, and let's put in some concrete numbers here. Let's say for a0, we put in a 1. For a1, let's put in 2. For a3, let's put in a 5. And for a3, let's put in a 2 again. Okay, and the prime field that we're going to be working with, this x mod p part, let's say that the prime number p is equal to 7. 7 is a prime number. So the valid coefficients that we can put in here will be the numbers between 0 to p minus 1, which will be 6. This is an example of a polynomial where each coefficient is an element from the prime field where p is equal to 7. Next, let's ask the question, what is the degree of this polynomial? Well, going back to the definition, the degree of a polynomial is the highest power of x with ai not equal to 0. In this example, what is the highest power of x where the coefficient a of I is not equal to 0? Well, the highest power of x where the coefficient is not equal to 0 is x raised to the power 3. So in this example, the degree of this polynomial will be equal to 3. Another question that you might have is, how do you evaluate this polynomial over the prime field? So let's say that we wanted to evaluate, let's say, x equal to 2. How do we evaluate this polynomial? Well, we're going to take this expression, and then I'm going to plug in 2's over here. And what you're going to do is evaluate this mod p where p is equal to 7. I just noticed that we're using p for the polynomial and p for the prime number as well. This is a little bit confusing, so I'm going to say that the prime number that we're going to be dealing with, I'll rename this as q. So going back to our polynomial evaluation, we need to evaluate this at mod q. There are several ways we can evaluate this expression. We can first calculate the inner part and then take mod q, or we can take mod q of the individual terms. So either we can do this, or we can do something like this. Evaluate each term mod q. In our example, this prime q will be 7. Let's put in the number 7. Okay, and then we'll evaluate each term one at a time. 1 mod 7 is equal to 1. 2 times 2 mod 7. 2 times 2 is 4, so mod 7 will be equal to 4. 5 multiplied by 2 raised to the power of 2. 2 raised to the power of 2 is 4. multiplied by 5, that's 20. 20 mod 7 is equal to 7 times 2 is equal to 14. 20 minus 14 is equal to 6. We'll have a remainder of 6. Okay, in the last term, 2 raised to the power 3 is equal to 8 multiplied by 2, that is 16. 16 mod 7. 7 multiplied by 2 is 14, so 16 minus 14 is equal to 2. Okay, so we evaluated each term one at a time. The last step is to add all of these up and then take mod 7 again. So this is equal to 4 plus 6 is 10, plus 1, 11, plus 2, 13, 13 mod 7, which is equal to 6 mod 7. So this was an example of evaluating this polynomial over the prime field where the prime number was equal to 7, and we evaluated at x equals to 2. We got back, the answer was 6 mod 7. Okay, so next let's move on to nth roots of unity. What does this mean? W is an nth root of unity if w raised to the power of n is equal to 1. Here we're going to be looking at FFT using the prime field. So here I'm going to mention that this is 1 mod q, where q is the prime number. Next I'm going to explain what the primitive nth root of unity is. W is a primitive nth root of unity if w raised to the power of n is equal to 1 and w raised to the power of I is not equal to 1 or I greater than 0 and less than n. Let's look at some examples of nth roots of unity and primitive nth root of unity. Consider the number w equal to 2 mod 5. So here the prime field that we're working with will be the prime number 5. This is, we're only considering the numbers between 0 to 4. Okay, next I'm going to show you that this w is an nth root of unity and also a primitive nth root of unity, but I don't know what this n is yet. So what I'm going to do is raise 2 to the power of I mod 5 several times from I equal to 1 to I equal to 8, and then we'll evaluate this mod 5. We'll try to find where this expression 2 of I mod 5 is equal to 1. So let's start by evaluating 2 raised to the power of I. 2 raised to the power of 1 will be 2, 2 raised to the power of 2 will be equal to 4, raise it to the power of 3 equal to 8, and so on all the way up to 2 raised to the power of 8, which is equal to 256. Now let's evaluate this mod 5. 2 raised to the power of 1 mod 5 will be 2, so 2 mod 5 will be equal to 2. 4 mod 5 will be equal to 4. 8 mod 5 will be equal to 3. How about 16 mod 5? Well, 5 times 3 is equal to 15. 16 minus 15 is equal to 1. So this is equal to 1 mod 5. How about 32? Well, 5 times 6 is equal to 30. 32 minus 30, we have a remainder of 2. So this is 2 mod 5. 64, 5 divides 60. 64 minus 60 will have a remainder of 4. 128, the number 5 will divide 125, and the remainder will be 3. And finally, 256. Again, the number 5 will divide 255, subtract that, and we'll have a remainder of 1. Okay, so this is our evaluation. Now let's try to find the nth roots of unity and the primitive nth root of unity. First, I'm going to highlight where the 1s are. So there's a 1 over here, and there's a 1 over here as well. Okay, so now let's scroll back up to the definition. A number w is an nth root of unity if w raised to the power of n is equal to 1. So we have 2 1s over here. We raise 2 to the power of 4 to get 1, and we raise 2 to the power of 8 to get 1 as well. This makes 2 the 4th root of unity and the 8th root of unity. 2 raised to the power of 4 is equal to 1, and 2 raised to the power of 8 is equal to 1. Okay, how about primitive nth root of unity? A number w is a primitive nth root of unity if w raised to the power of n is equal to 1 and w raised to the power of I is not equal to 1 for I greater than 0 and less than n. So let's apply this to our number 2. Is 2 a primitive 4th root of unity? Well, 2 raised to the power of 4 will be equal to 1, so it satisfies this condition. And how about this condition? For I less than n will be equal to 4, is it not equal to 1? Well, let's check our evaluations. So we need to look at 2 raised to the power of I up until 4, excluding 4. And we see that all of the evaluation are not equal to 1. So this makes 2 the primitive 4th root of unity. How about is 2 the primitive 8th root of unity? Well, again, let's apply this definition. 2 raised to the power of 8 is equal to 1. So 2 is an 8th root of unity. Now, is it a primitive 8th root of unity? The other condition that it needs to satisfy is this part. So we need to look at our evaluation from I equal to 1 all the way up to I equal to 8, but less than 8. So that's 1 to 7. And we need to make sure that 2 raised to the power of I is not equal to 1. But looking at the evaluation, we can see that 2 raised to the power of 4 is equal to 1. In this case, it doesn't satisfy this condition, so 2 is not the primitive 8th root of unity. Okay, that completes the definitions for polynomial, degree of polynomial, nth root of unity, and the primitive nth root of unity. In the next video, I'll show you two useful properties of root of unity that we're going to need to understand FFT.